I'm Gyuwan from Kaist AI, and I'll be talking about SSMix. This is a joint work with Gyuwan Kim and Jimin Park. And I provided another presentation to fully explain our experiments. So this is an unofficial version. So the table of contents would be to explain what mix-up is, and then our methodology and how we experimented, and finally the analysis of our methods. So first, what is mix-up? Mix-up is first presented in the 2018 iClear paper, and my work starts from this mix-up. So what mix-up is that mix-up generates samples by a convex combination of two samples, and it's currently on classification task. In the original paper, it is explained that in order to minimize the vicinal risk minimization instead of empirical risk minimization, we need to make additional samples that is outside the original training data samples. So in order to regularize and generalize neural networks. And as far as I understood, this is the picture I drew after reading the paper. So if we take the black dots as training dataset and the green one as the original model's decision boundary between other labels, so this could be label 1's space, and this could be label 2's space. So this green line could be the line formalized after the empirical risk minimization. And after we apply mix-up, we make a virtual example, the purple one, by linearly interpolating these two training examples, and make labels according to the lambda that we sample from the beta distribution of alpha. And by doing so, and then we train the model. By doing so, we get some kind of regularized decision boundary, which could be the red one. So this was the official code that we found for the mix-up repository. So if you look at it, you first sample lambda by the beta distribution of alpha. Alpha could be fixed, and you make a virtual dataset X and Y according to lambda. So you mix up in linearly interpolating in lambda %, and then you forward the loss and Y to the model. Additionally, with the if we sample alpha and lambda could be 0, so when lambda is 0, it is the same as feeding the original x2 and y2 into the model. And when lambda is 1, it is same as feeding the original data sample x1 and y1 to the model. So this was the picture. So after applying mix-up, the decision boundary kind of smooths this to like linearly, as you can see in this picture. So this was the original result that we found in the original mix-up paper. And one thing to note that it performs very well on image datasets. However, in some kind of dataset like speech dataset, where the datasets is kind of sequential and the total size is not limited or fixed, applying mix-up doesn't always help, as you can see in this example. And one other thing that we noticed is that performing mix-up with all kinds of classes and with randomly picked samples exceeds the best performance. So like just random pairs, mix up between random pairs was better than mix between k nearest neighbors, and mix up between all classes was better than mixing up between same classes. So we got the intuition here. And then after research about previous research about mix-up, we found out that there were two mainstream tasks for mix-up. The first one was hidden level mix-up, and the second one was input level mix-up into images. So mix-up was very much explored in the image area. And if you can see here, so hidden level mix-up, one kind of mix-up work done by the hidden level mix-up was manifold mix-up. And in the manifold mix-up, it is stated that the hidden layer representation was kind of more linear than the original mix-up, and then it affected the input level classification decision boundary to be more better. So they achieved more great results. However, we found out that input level mix-up was more efficient and performed better than input level mix-up, such as cut mix, puzzle mix, or attentive cut mix, where they directly applied mix-up or variants of mix-up, like this or like this, into images. So, after investigation, we thought that applying mix-up directly into the input level could be more effective also for text, other than applying mix-up in the hidden level. However, there were some problems when we apply that into directly into input level for text because of the different characteristics they have with respect to images. So the first problem was, so how do we define the convex combination of inputs when the input was represented as a sequence of discrete tokens? So with respect to the fact that pixel in images, the pixel can be treated as a continuous variable. However, we have to first convert the tokens into input IDs, and the input IDs are discrete, right? So like I could be represented as 3 or 102 as input IDs, but they cannot be represented as like 52.51 or something. And we can also view that the image pictures are kind of linear, but in the value, but input ID 4 doesn't have any relation to the tokens that have input level 3 or tokens that have input level 5. So there's no linear kind of characteristic. So that was kind of difficult. And also, the length of the two sequences that we use for mix-up can differ in length. So if we look at the previous work, for example, if we have to apply mix-up on the hidden level, they just appended pad to the shorter sequences to make the lengths become the same. And also, the problem about the convex combination cannot be defined. Previous work tried to solve this problem as applying mix-up on the hidden level. And so for example, on the encoder hidden layer or at the embedding layer. And third, sentence structure may be destroyed if we just directly apply input mix-up into the text. Unlike pixels. So we need to solve these kind of issues. And as I explained in the challenge point 2, there was only hidden level mix-up applied on text. So for example, on SSMix, on the partial work on the mixed text paper, they applied hidden level mix-up on the encoder layer. And for embed mix, they applied hidden level mix-up onto the word embedding, so like the word embedding or sentence embedding layer. And in our work, so we first proposed the input level mix-up on text by solving those kind of problems I addressed in the previous slides by preserving the locality of two original texts by span-based mixing, and keeping more tokens related to prediction by computing the saliency scores of two texts. So if you can see in this example, we replace the most salient span from one text into the least salient span from the original text, and we make another virtual data set, and the span that we replace it is the same. It is fixed by the predefined lambda. So for example, in this example, the token length was 10, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if we define lambda as 0.2, 20%, meaning token length 2 becomes the span length. And we replace it and make another virtual data set and make lambda, the label, according to the lambda, predefined lambda that we assigned to. In order to compute the saliency scores, we use the gradient-based methods. So, as you can see in this code, we computed the gradient with respect to the classification loss and computed the embedding gradient and applied the L2 norm for that. And for mixing text, as I already explained, we computed the least salient span and replaced it to the most salient span, and the span length is calculated as the minimum length of the original lambda token, or the total length. So the total length of the span to be replaced should be larger than the span length, right? So in order to get rid of the exception, we added this. And also the original text length could be very small, so that the output of this could be like 0. And we don't want that because we want to make virtual training examples. So we added the restriction to be at least 1 for the length. And for mixing labels, since the token is discrete, the predefined lambda could be different. So the output lambda could be different from the predefined lambda. So like if the original token length was 9 and the predefined lambda was 0.2, the output span would be 2, but the output label should not be 0.2, but be rather 2 divided by 9, right? So that was the procedure explained for this. That's that we recalculate the lambda after the output formulated by the real output token ratio, and then we assign that. For paired sentence tasks, we applied mix-up individually by sentence. So for example, if the original data set consisted of 2 sentences, we first apply mix-up on the first sentence, and then we apply mix-up on the second sentence, and then we individually add the virtual data set outputted by this sentence example. And when we calculate the lambda, we calculated the total length of total tokens by the output on top of the total length of the spans that was replaced. So in this example, the lambda could be calculated as the total span length, the total token length for the sentence, which is 5, and this is for 6, and the span length is 1 and 1, so the output would be 0.18. So we applied the 0.18 into the output label. Explanations of the following will be at the next video.